And so exciting to see so many of you here. I did wonder whether you'd all come to see the person that was introduced falsely, but hopefully you're all here. I mean, we actually got turned away at the door, so there's no more room. I said, well, I think you might want us three in here. So fortunately, they did let us in. But, I think it's a real testament, actually, to the Jaipur Literary Festival that, I've been coming to the festival for many years to invite scientists along. Because you might think, well, what are scientists doing at a literary festival? Isn't this just about poetry and novels and things like that? But I think the Jaipur Literary Festival realized very early on that scientists have amazing stories to tell. Stories that tell us about where we've come from, where we're going to go next. Some of the stories that we'll start exploring in our panel. So, and I think the fact that they've been so successful in promoting these scientific stories is testament to how many of you are here today. And I can see some young people here as well. And for me, that's important. These stories, for me, are what made me into a scientist, somebody telling me stories. So I thought we'd just start with our two panelists, just saying, well, what was it that brought you to choose to do science as opposed to becoming a novelist or something else extraordinary? So why did you become a scientist?
Exactly like you said. There was a scientist from Newcastle upon Tyne who came to my university to give a lecture on volcanoes and the wonderful colors of the lava and the kind of display he had told me that this is exactly what I want to do. I want to look forward to studying something in deep, to go into the depths and the profound understanding of why the universe is what it is and why does it matter.
So somebody telling you stories, exactly.
Absolutely, absolutely.
Lit the fire. And for you, Geraint, what was the inspiration?
Inspiration was, I guess, just looking at the natural world and eventually thinking to myself, well, how does this stuff work? And I guess at some point I came to realize that we do have a mechanism whereby we try to put together the rules of the universe and how everything behaves. And I never actually thought I would be a scientist, but I was always kind of interested in this idea that we can work out the underlying rules, and from that, where did we come from and where are we going? So again, just trying to understand the universe around us.
And so you've both chosen rather different ends of the scientific spectrum, the incredibly small particle physics to the very big astrophysics. So what drew you to both those ends of the spectrum?
I think if I can bring the analogy of a large onion, and if we were to keep peeling and peeling and peeling and keep going inside the onion, in the end you would still have a cell that you can subdivide and keep going inside. It's exactly the same way the universe functions. We have no idea of how the universe worked before, and before we understood some kind of theories that came along the way. And of course, there have been so many scientists who have been contributing to the theory of the universe and to understanding the secrets of the building blocks of matter. So the onion still is not completely at the most fundamental point, because when the Greeks called the atoms an atom, it meant indivisible. And now we all know very well that the atom can be divided, and there are electrons and protons and neutrons and quarks, and who knows what's next?
Well, exactly. Who knows what's else? I mean, if you look back in history, I think every generation thought that they'd hit the last layer of that onion. And I think we still believe that, now we're back down to electrons, quarks, neutrinos, and we feel like that's the building blocks. But, there is the hint, are these things strings maybe that make up these particles? I mean, that's one of the challenges of science. Will we ever know that we've reached the kind of, the answer that explains it all?
Well, if I can bring in a quote here, which is rather known, I think, to the audience here. In 1945, the chairperson of IBM said, "The world needs about 5 computers." So, today we do not know what we do not know. So we need to remain humble. I think that's what big science teaches us, where we work together in collaborations with thousands and thousands of people from all over the globe, and we come together to do these experiments. And we need to remain humble to the fact that definitely we know a very tiny fraction of what can be known.
And Geraint, you went, I think you did do some work at CERN originally about the very small as a student, but you chose the very large. So what flipped you to add layers to the onion, I guess?
I guess when I found out about science, I was drawn into physics because I thought, what are the fundamental bits of the universe? And it seemed to me that the interesting places were the very, very small or the very, very large. And it really was a toss of a coin about which path I was going to take at the end of the day. But working in the large-scale universe and asking those big, big questions about where did this universe come from and what, was there anything before? That's what drew me away from the very, very small into the very, very large. But they are connected. It's not like that we're two separate fields. There's a lot of crosstalk between us.
Yes, I guess issues of dark matter is a kind of cosmological question, was discovered because we realize there's something pulling the universe in ways that we don't understand. Yet I guess that's a question about, well, what are those particles that make up dark matter? So is that the sort of connection between the two?
Absolutely. I have a small label that I put on myself, which is astroparticle physicist. Uh-huh. And so there's a
trying to have it all.
Yeah. So there's a large number, a growing number of particle physicists who are turning towards the sky. There's so much you can do at the Large Hadron Collider, and you need to put in more and more energy to get more and more interesting results out. But the universe already does things at incredible energies, and so people are saying, can I take what I've learned already and apply that to some of the things that we see on the sky? So astroparticle physics tries to essentially really bridge that gap and answer those questions. They said, what is dark matter? We know that there's more stuff out there which is not made of atoms like this by a factor of 6 or 7, and we have no idea what it is, but it dominates the universe. So again, it's those kind of questions that keep us in, brings us to work in the morning.
And so what would you say were the essential differences between the way that you do science? I mean, particle physics, you've got these big experiments going on at CERN, but with the universe, how do you do experiments? I mean, is it just a very passive as opposed to an active engagement as a scientist?
Yeah, so in astronomy, we're mostly observers, right? It would be nice if we could manipulate the universe, but it's a lot bigger than us.
Maybe not, actually.
Yeah. And so, yeah, we observe, and what we try and do is we try and collect information across all radiation bands, from gamma rays down to radio waves, and also from particles that collide with the Earth. We try and collect those as well, and from there infer what's going on in the universe. So we're presented with one universe, and we're trying to work out what is going on with that universe, but as you said, we cannot manipulate it.
Well, Archana, you do a lot of manipulation at CERN.
I mean, so this is the accelerator that we have in nature, where you have particles coming from the outside world, and we are trying to understand that from the Earth about the cosmos. What we are trying to do is to recreate the conditions of how the universe was created. So obviously we are not going to create the universe itself, right? We are going to do that, albeit on a very, very, very minuscule scale, in safe conditions, underground, and we will study how the universe was born. And the kind of particles that he mentioned, like the dark matter particles, as we all know that we just know barely 5% of the whole universe is made out of matter particles, like of which me, you, and the table is made of. So dark matter particles could be created when we are recreating this Big Bang under in our laboratory conditions. So the big difference here is that we need data, because we just might be able to have a candidate particle of dark matter created, and then and that possibility is like finding one gold grain of sand on all the beaches around, where you have ever been. So what do we need? We need data to actually siphon out or sift through, whittle down to that dark matter particle.
But I guess data is also an issue when we go to astrophysics. I mean, we have a project in Oxford called Galaxy Zoo, because basically there were so many images of galaxies coming in that there weren't enough scientists to actually look at these. So we asked the public to help us identify spiral galaxies, and they even identified a new sort of galaxy, the green pea galaxy, which all the scientists were saying, oh, just ignore that, it's an anomaly. And so, I mean, data, and I guess we're going into a period of a lot of data coming from the new telescopes that we're sort of using to look at the sky.
Yeah, absolutely. I mean, the secret is that we're terrified about the amount of data we're going to collect. So if you see me wandering around, I've got a blue bag with SKAO written on it, which is the Square Kilometre Array Observatory, which is a telescope being built across South Africa and Australia. And in fact, each telescope is going to have to essentially have a supercomputer attached to it to work out how much data we can throw away, because we can only keep a little bit of the data that flows. So we are facing this absolute avalanche of data, and we're trying to have to sift it before we can even work with it. So yeah, data is the name of the game at the moment.
One of the big themes, of course, which is running through this festival and many festivals, is artificial intelligence. I mean, I've got 2 events that I'm doing over the next 2 days on the subject. But I guess this is a place where artificial intelligence, which is very good at spotting patterns in data, significant messages, might be a very useful tool for both of you.
Yes, absolutely. I mean, in astronomy, we've faced this data problem for a while, and so we were using the precursors to artificial intelligence before it really was called artificial intelligence.
Which is humans. No.
Well, no, neural networks and large data and all that kind of stuff, and it's all morphed into this entire picture of AI. But yeah, we need that to work with these data sets. It's all multidimensional, and we're looking for things in there. For a human being, it would take a lifetime maybe to find one thing, but of course, we can get machines to churn through this data a lot more efficiently.
Indeed, it's the same thing for us, however, on another scale, because our collisions that happen on the collider are 40 million times a second. So we are collecting, I think the largest data set on the planet has been collected. We crossed 1 exabyte of data. I mean, how many zeros are there? I think the younger ones here might know, but it is quite a challenge, and we also need to have triggers and algorithms while taking the data, so that within the 25 nanoseconds, when we are making decisions, that's how the artificial intelligence and pattern recognition actually evolved, I must say, because that is a precursor to what AI has become today. We've been doing research for the last 25 years with data governance, pattern recognition, like you already said, and in fact, the World Wide Web, I think Sir Tim Berners-Lee was here, and that was also some way looking forward how to deal with data. And today, we can't imagine the world without the World Wide Web. And in fact, we do not know the kind of things that are coming out from our experiments that will then reach to the society and in your pockets at some point, where you will say, oh, was there a world without the World Wide Web?
Mm. Now, this session is called the God Particle, which might be what drew so many people into the room, I'm not sure, which is about, probably one of the biggest discoveries that was made in the last 20 years, 30 years. So we should probably address what this particle is. I think actually it should have been called the goddamn particle, because the person who was trying to write a book about it was saying it's so elusive we can't find it, and then the publisher crossed off the damn and it got left as the God particle. So I think many scientists really resent this term. It has got nothing to do with God, or does it? I mean, it's interesting. So I'm going to give you a little challenge, which is one that William Watergrave, our science minister, who was working under Margaret Thatcher at the time, and this was before we knew this thing might exist, but it hadn't been discovered, and a lot of people were asking for money from the government to fund what's happening at CERN. So the science minister, William Watergrave, offered a challenge, which is how to a lay person do you explain what the Higgs boson is? So this was an interesting challenge, sort of really kicked off a lot of scientists trying to engage with the public about what this thing is. So what's your dinner party kind of take on how you tell your neighbor who says, oh, I know nothing about physics,
all right,
the Higgs boson?
All right, so first of all, thank you all for coming here, and imagine that we are at a party, right? and we are having a good conversation with each other. You're not really listening to me, but you're talking to each other and freely moving around, right? Maybe on all the grounds that are here, and you've got many of your friends. Nobody's stopping you from moving from one place to the other. But then suddenly there's a rumor of a big star who's going to arrive here. It's already happening at the speaker lounge, by the way. So, who could be that big star of today in India? Ranveer Singh? Shah Rukh Khan. Okay, Shah Rukh Khan. Everybody knows Shah Rukh Khan, huh? So imagine that you have not seen him, but there's a rumor that Shah Rukh Khan is coming here. And what would happen at that moment of time? Just think about it. There are several gates of entry into this venue, and you might want to scratch your head saying, which gate would he be coming from? And I would start migrating there depending on my fan quotient of how much I like Shah Rukh Khan. Because there could be people who say, oh, Shah Rukh, so what, you know? But then there would be people, Shah Rukh, you know, they will push people and they will go to that gate number 3 or whatever it's announced that he's coming from. So these people, they become suddenly heavier. Do they? They become heavier because they are trying to move and push people and they are not able to move, while there are other people who are relaxed and not really interacting with this information about Shah Rukh Khan coming here. And that is the moment when all the particles that are all of you, at that moment of the Big Bang, actually acquired mass. Higgs is like a star. And I might remind all of you that half of the universe has the name boson allocated because of Satyendranath Bose, who worked with Einstein, and so thank you. The whole universe, half of the universe is bosons, the other half is fermions. And the Higgs boson indeed is the star, like Shah Rukh Khan, who appeared at the moment when all particles were moving around freely, and when they started interacting with the Higgs boson, or the Higgs field, I would say, they acquired mass. So I say that the universe had possibilities, had energy, but it mattered only when the Higgs boson appears.
I thought that was very good. Let's give a round of applause for, yeah.
Makes sense?
Now, you're both actually fantastic scientists, but also fantastic communicators as well. I mean, Geraint, what's the sort of challenge for you of trying to explain some of the difficult concepts to the public? I mean, do you have sort of ways that you do it, which kind of bring some of these very difficult concepts alive?
Yeah, there are many challenges because, of course, I myself and Archana here, we work in a world of mathematics and science speak, and I want to get across concepts to you like how the universe is expanding, what does expanding universe mean, etc., etc. And we have to work out how we can turn mathematics into pictures that can get the ideas across. And it's a bit of an art form because a bad analogy tells you nothing really. So it's like, as we were just talking about the Higgs boson there, you have to think about the picture that you're going to use and relate that to the concept. And it's not always easy, especially when you get into the really complicated aspects of cosmology or particle physics. So it takes a lot of thought and appreciating your audience and thinking about how you can relate those concepts to what picture they might see.
So the Higgs boson was probably one of the biggest discoveries in particle physics. What would you nominate as the big discovery that's happened in the first quarter century in astrophysics?
Well, there's a few to choose from, but I think it has to be gravitational waves. Yeah, so these are now, they were predicted in 1916 by Einstein. They were discovered in 2016, so only it took a century worth of work till we could discover them. But they opened an absolutely new window on the universe, right? So most of the information we get about the universe, we get from radiation, from light and X-rays and gamma rays, etc. But there are lots of things that go on in the dark which don't emit light, so we do not know what's going on. Gravitational waves, which are formed when you basically have a really violent event that shakes space and time so hard that it causes ripples that travel across the universe, we can now pick up those signals. So the first gravitational waves that we detected we realized was two immense black holes, like each was more than 10 times the mass of the sun, colliding together. And they are violent events. They shake space and time, and we can now detect these over billions and billions of light years. So a completely new window on the universe, and in the 10 years since we started observing them, we've already revealed that the dark side, the darker side, the stuff that we cannot see, there's an awful lot going on that we don't understand. So yeah, a new window on the universe is always good.
And was that due to a new sort of telescope, as I understand, that was able to pick up the kind of, the fine detail of a gravitational wave?
It all comes down to sensitivity.
Yeah.
So essentially what you're trying to detect is space and time rippling. And space and time ripple, but in very, very tiny amounts. And the question is, how do you detect that? You don't feel it with your body as a gravitational wave comes through you. So you need to take something that you can measure precisely and see if that sort of measurement changes by a tiny bit as the wave comes through. And it came down to technology. The LIGO telescope, the Laser Interferometry Gravitational Observatory, 2 arms, both 4 kilometers long, a vacuum, and you're bouncing light back and forth. So this is a 4-kilometer length separation. And the sensitivity got to the point you could measure 1,000th the width of a proton, which is a subatomic particle. And it was once we could get to those sensitivities, then we entered the realm where we could detect these gravitational waves. But as I said, it took 100 years of basically experimental advances and pushing noise down further and further before we could do that.
I don't want to big up my subject too much, but mathematics, of course, is key to both of these predictions. I mean, we sort of knew the Higgs boson was going to be there before we observed it. We predicted the gravitational waves, and often that does come from mathematics. So do you think mathematics is, a fundamental language for everything that you do? And the answer is yes. But
the answer is yes. Yeah. This is a complete side story. So one of the things that happens when you're a cosmology professor is that out there in the general populace, there are often retired engineers who have ideas about how the universe works. And they send you their ideas, and they say to you, oh, this is my idea. All I've got to do is work through the maths, and I think I will revolutionize cosmology. And you have to write back to them and say, no, you need the maths. The maths is the physics. The story around it is the story, but it's all written in the language of mathematics. So for all of cosmology, start in the morning, it's equations and working with maths.
I'll give you money later, don't worry. Yeah. And for you as well, I guess, all the predictions of so many particles came, well, first of all, from seeing these things, but then it sort of implied there should be others as well.
Thank you. It goes hand in hand, to be honest, because it is a prediction that comes from theory. All of you have heard about antimatter, and if not, then you can imagine that when the universe was created, then matter and antimatter should have been equal, because the one equation, the mathematical equation that everybody knows, is E is equal to mc squared, right? So it should be an m plus and an m minus, right? And this was predicted mathematically by Paul Dirac. And then the antimatter was observed in nature.
But everyone thought he was just ridiculous. Okay,
Exactly.
So there's a kind of negative solution, but
Yeah.
that's just maths.
Yeah.
And he said, no, I think that this might exist.
I know. And that's why it's extremely important from the very basic classroom in the high schools and secondary schools and colleges to be very strong in mathematics, relating it with real life, Because if we do not, then we study these very abstract equations and we don't even understand. We keep saying, are we going to ever use them? Believe me, that's what I said. And then when I remember years later, when I started my particle physics journey at CERN, I went back to BITS Pilani. This is a place in Rajasthan, And there is a museum, and you will see that there's a bucket of Rajasthan sand with a hole on the bottom, and you can go there and just push it and leave it. So it will create some kind of figures on the floor, which are called Lissajous figures, that I learned in college, but never knew how they can be used. And now cathedrals and temples and all the designs that you see on top, now all you see are Lissajous figures over there. Once you know it, you can't unsee it, you know. So I believe that mathematics is extremely important, and teaching mathematics from a very young age, linking it with the universe, is extremely important.
Very good, yes, absolutely.
Thank you.
But I guess one of the criticisms that comes to fundamental scientists as well is, okay, it's all very exciting to have these big stories of where we've come from, where we're going to go next, but how is it useful for me as a person on the street? So is the physics that you're doing at all useful? Does that matter?
You want to go first?
Today, not really that useful. Although I train PhD students, and they study the universe, but not all of them become professors. But they're mathematically trained, they're trained in computers, and they go off into consulting and banking, etc. So we are training an educated society. I think this is one of the important things about blue sky science, is that we cannot predict what the outcomes are going to be. And the example that I really like is that at the end of the 19th century and into the 20th century, physicists were wondering what matter is made of. And as they peeled matter apart, they realized that atoms are composed of smaller particles, and inside the nucleus there are protons and neutrons. And at the time, I'm sure people said, well, that's interesting, but what's the point? But one of the most advanced machines for tackling cancer these days is proton beam therapy. And the people the people that basically discovered the proton, they weren't motivated by finding a cancer therapy,
Absolutely.
right? But the outcome at the end of the day is that we have new therapies that are being used around the world.
Excellent, yeah, thank you. So proton therapy actually has been pioneered by CERN also, and if I can just bring it forward. And hadron therapy also is very much a big need in India, Now, but coming to your question about why should we care? Why should the layperson care that we fund so much money, so much as if into big science, First of all, the cost of not investing is huge. We are building capacity. We are building capacity for banks. 90% of people who do data analysis on physics experiments, they go to do risk analysis in the financial world. The banks are sitting there to hoover them up, In addition, I would say that all of us have been struck by COVID, which came like a bolt from the blue. We had no idea what it is, and every one of us had a personal experience of the world coming to a halt. Imagine no WWW. Imagine no therapies, no drug discoveries. Imagine no microscopes or the scanning electron microscopes with which we could see the virus for the first time. And all this is coming from the humble physicist laboratory. So when we are doing the science, we are not putting, the equations in the drawer. They are coming to you directly or indirectly the moment we are hit by a crisis. And this is, of course, special, because the first, let's say, drugs that were, and the vaccine that was made, there was a folding technique that used the web very intensely, and that was also pioneered by CERN and given to the world for free. Now, if you look at, for example, if you go to the hospital, X-rays, where do they come from? Everyone remembers Marie Curie, right? She gave her life, and her grave is still radioactive. So these things, they look very esoteric when we talk about it, but when we go through the securities in the airports or go to the hospitals, as I was mentioning, MRI techniques, the magnets that we are using today, there is a market of $3.8 billion for superconducting magnets that have been a spin-off from CERN to make the Large Hadron Collider. So I can go on and on, but I guess
I think it's important in a way. I think it's important you do, because I think one of the tragedies, of course, is governments are very short-term in their planning and thinking, and they don't understand these unexpected consequences come out of funding science for its own sake, and then you get these incredible spin-offs. So I think it's very important that we celebrate these stories of just pursuit of pure knowledge, giving rise to amazing discoveries that impact us all.
can I chuck in another anecdote?
Yeah, go for it.
So there's a famous anecdote that Michael Faraday was working in his laboratory one day, and he was showing off effectively the first electric motor to a minister and explaining about what electricity was, right? And the motor's going around. And the minister said to him, you know, this is all very interesting, Faraday, but what's the point? And Faraday's response apparently was, probably never happened, one day you may tax it, right? So this is can you imagine the modern world without electricity and electric motors, right? I mean, they are everywhere. But they came from Michael Faraday trying to work out how this stuff works.
Now, we've been celebrating a lot about discoveries of the past, but I wonder whether we have something called the standard model of particle physics, the standard model of cosmology, which all of the experiments are kind of confirming. But I wonder, has physics got stuck in a news story? I mean, do we just kind of know what's happening? And are there any big stories waiting out there to completely change the way we're going to see the universe? Or are we just going to keep on confirming that the models that we've got are the correct ones?
Okay, so again, picking up from you, the electron, when the electron was discovered and then electronics and semiconductors and everything came along in your pockets, how much did we have to study to get there? How much research was needed to get there? Every discovery today is a calibration for tomorrow. So if we have discovered the Higgs boson, it needs to be studied in the greatest detail. It needs to be understood on how it interacts with other particles. How does it behave? And are there other bosons like that? And there is a lot of still open questions on the Standard Model, which we do not understand as yet. Like we said about antimatter, we spoke about dark matter, dark energy, and of course, the model, the theory of everything, for example, which encompasses all the forces of nature into one equation. I'm sure you have seen many physicists wearing T-shirts of the Lagrangian of the Standard Model, but you know, it is a tweaked equation, if you know what I mean, you know. So we need to get to the point of understanding more. I wouldn't say everything, but we need to understand more. We do not understand gravity. So bringing all these questions together in a unified theory is the quest. And the Higgs boson was discovered in 2012. Today we understand it much better. We have moved from discovery to precision, and we are doing precision physics right now. We are going to stop the LHC in July this year for 3 years, and we are upgrading it with more strong magnets, more intensity, and we'll be able to take in 1 year all the data that was taken in the last 15 years. So that's the kind of power that the HL, the high luminosity LHC, is going to bring for us. And then who knows what's in the offing? We have no idea what we will find over there. So it's not only about the physics, it's also about data, management, governance, AI, and all that we already said. But engineering, I mean, it is mind-boggling, awe-inspiring to see the scientists and the engineers from all over the world come together and build something that is a single unit of an equipment of 27 kilometers. And then bringing it up to speed to handle these kind of datas and events and the matching between, I mean, try throwing a little marble in a pond 30 kilometers away. That's not this challenge I'm talking about. This is like throwing a marble to New York somewhere, you know. So the challenge, the electronics and the everything, I mean, the triggering and the, let's call it instrumentation challenge is so huge that finding solutions actually is building the infrastructures of tomorrow in countries like India, for example, where I do believe that long-term vision and long-term thinking for capacity building in every aspect is actually being unleashed as we speak.
And Geraint, how about for astrophysics? I mean, I mean, I do remember a change in the model where we suddenly understood that the universe isn't just expanding, but it's accelerating in its expansion, and that kind of changed the way we have to think about the way the universe is evolving. Are there kind of going to be, do you think, what would be the next big news story that might hit us in the physics of the very big?
prediction's very difficult, right? Especially about the future. We don't really know. This stuff comes from left field. So this story you told about the discovery of dark energy at the end of the 90s, nobody was expecting it, and it basically changed the way that we had to look at the universe. So as data comes in, we are going to have to basically take a look at our model and just make sure that it's doing what we think. But it has holes in it, right? We do not know where the universe came from. We can measure the evolution of the universe back to some ridiculously small time after where we think it began, but was it really the beginning, or was there something else before that? And part of the reason we can't answer these questions is that particle physics and cosmology, we speak different languages, and we cannot talk about the very small and the very large in the same sort of maths, and this has been a problem for 100 years now. Einstein, on his deathbed, was working on trying to basically smooth over, he failed, and we still feel like we're a long way away.
So one of the challenges, it seems, that we've got ahead of us is how to merge you two together to make a single scientist who understands both the small and the very big.
Yes.
So a chance now for some questions from the audience, and look at those arms go up. So do we have a microphone that, I'm going to start with this young chap down here who might well be the next scientist who unifies these two theories. Hopefully these stories have been inspiring him to think big and small.
Hello, I am Aram. The most fascinating thing about space and science I can think about is wormhole and singularity. But for you, what is the most fascinating thing about space or science?
Well, for me, one of the most fascinating things is that we have black holes in the universe. Now, these were written down by Schwarzschild back in 1916, and everyone thought, well, this is a crazy thing. He said that there was places in the universe where things have completely collapsed, gravity becomes infinitely strong, and everyone just went, well, that's just maths going a bit crazy. But then in the 1960s, people started to look in the middle of galaxies, and they were going, there's some really weird things going on here. And there was huge amounts of energy coming from tiny, tiny places. And we've worked out that can only be a black hole. And in fact, it turns out there's not just one black hole in the universe. We've now seen that there are probably trillions of them. And so the fact that these things exist, they were like derived mathematically again a long time ago, and they exist in the universe. It makes me wonder what else could be out there. We haven't explored all of the mathematics yet. So black holes for me are really, really cool. But I think things like wormholes might actually be a possibility, that we might be able to travel huge distances by bending space and time enough. So hopefully one day you can work that one out. Yeah.
And your choice of we've covered many, but...
Yeah, I mean, for me, it's fascinating how science fiction writers and authors write amazing stories like Isaac Asimov. And then in the end, it becomes true. And that is what I'm inspired by. And I would also encourage you to read more about science fiction. And believe me, in my lifetime, I've been very fortunate to see such transformational things happen that I could not believe when I was a kid like you.
And I think that's the importance of imagination, that it's certainly important to be a novelist, to have a good imagination, but to be a really great scientist as well. Imagination and creativity is absolutely key to be able to imagine the impossible and then show why it is possible. Yes. I'm going to take the woman at the back there in the whites. Keep your hand up. Yes, exactly.
Sabko namaste.
I shouldn't gender people because it's always a big mistake.
Koi baat nahi.
Even the best times, but yeah.
So as you spoke on, perhaps like the holy grail of current physics would be the discovery of the graviton, right, which is proving very elusive. Are you all aware of any current or upcoming experimental setups that you feel optimistic could do that? And conversely, are there any experimental setups that could conclusively prove that gravity is not quantum?
You want to take it?
It's a very difficult question to answer. Yeah, so the only place that we currently think that we could find the quantum signature of gravity, i.e., is there a single language that we're written in, is when black holes collide. So what would happen is that that quantum nature would be written into the way that the signal that we get from these black holes. Now, the problem that we have is that that signal is going to be very, very subtle, and the data is still quite noisy. So people have proposed, we need the next generation of gravitational wave telescopes, and they are planned. I believe India has plans for one. Yep. And so you get more and more of these telescopes such that we can get better and better data. People have tried looking, but at the moment there's no sort of apparent signature in what they've seen. But as I already mentioned, sometimes answers to these questions come from left field, and somebody will do an experiment one day and just go, oh, that doesn't quite behave the way that I expected it to. So gravitational waves are the hope, but left field might actually be the answer.
Oh, we're running out of time, so I'm going to choose one more question, which is going to be this woman down here. Great.
You have a question.
Oh, thank you.
Excellent.
Yes, my question is this. As a layman, as somebody who who is not very much into science, I wish to locate myself in my world as far as possible, perfectly. Now, there are some things, I want to be a rational person. There are some things which are very obviously rational, and I can subscribe to them. There are some things which look obviously irrational. I stay away from them. But there is a whole lot of mid-ground where I'm not able to take a decision about whether these kinds of beliefs should be called rational or irrational. For example, when I think that everything can be decided by physics for me, and if I trust in the scientists, I will know who I am. But when I look at things like infinity, yes, I'm just trying to, if I look at questions like infinity, I feel I can't really comprehend them. So what I'm trying to say is that when I look at like supernatural answers or spirit or
Brilliant.
whatever, X, Y, Z.
Yeah, great. Because we're running out of time, I'm just going to, because I think, one of the big questions at the heart of that is, can physics explain it all? Can physics explain it all? Yeah, go for it.
So science needs evidence, and questions like those, when they will be proved, like 30 years ago, 40 years ago, I would not believe that I would be able to make a phone call to New York without a cable. And that's where all this quantum and science comes true, from the equations to reality. And then science stops, philosophy begins. Right?
Let's give our storytellers a great round of applause for some wonderful stories of science. Thank you very much.
Yeah, very quick question. Has physics explained two things, time reversal invariance, and two, consciousness?
Oh my gosh, have you got another hour? Yeah. So time reversal and consciousness in minus, I suppose we're going to use negative time here, but I think have you got a quick answer for that? Okay.
Consciousness, who knows? We can't even define consciousness properly. Time reversal, maybe, but it's not completely solved. Maybe, but not yet. So look, I need a job, I need money, so I'm not going to solve every problem today, right? So,
anyway, let's give them a big round of applause again. Thank you so much for coming.